Okay. Good afternoon. I'm Irene. I am from the University of Padova, and this is I'm presenting now my PhD project. A little bit of table of contents. I will briefly introduce the project and then talk about really shortly, because we already had an introduction about that, about the environment on where the drone should operate, along with some science goals we posed on that. And after that, I will pass to the how and why we choose legs for the drone, and on some preliminary calculus about the vertical descending, along with a really preliminary mission design concept, and finishing with the next steps for the project. So the purpose of the project was to design a legged drone that could support in lunar and planetary exploration, venturing into Martian and lava tubes, along with assisting in terrestrial operation as well, and also in the future, maybe also astronauts on a lunar basis. So to do this, we choose to do a legged drone because in this way it could maximize the benefit offered by the ground segment and the aerial segment. And one of the goal, the main goal of that was to design it the more compact possible, as we will see. In this way, it could be possible in the future assembly that with 3D printing or additive manufacturing directly on site. So the environment, the primary environment in which you should operate are lava tubes, which are, as we know, caves created by flow low viscosity lava. And what we already know that they are relevant because they could represent a good place for a future habitat on the moon, due to some reason like the dimension or the shelter from planetary radiation, or like a daily and seasonal variation, like more controlled with respect on the surface. But to study this kind of environment, we pose some science goal to also define the payload, the sensor suite for the preliminary sizing of the drone. The main three are the mapping of the conduits to create a similar 3D model of the underground conduits to understand, of course, dimension and potential pathways, done with some SLAM techniques, also with LiDAR or stereo cameras. And another one is the quantification of radiation penetration to assess the potential habitability inside these lava tubes. And the last one is the quantification of relative humidity and temperature variation, also to assess habitability, and also to understand more about the microclimatic condition inside this type of environment. So why legs? We know that respect with wheels, legs are more complex, require more complex, complex because they have a numerous. They have more actuators, and so their control can result more complex. But they are really versatile because, and considering the type of mission, it could be the best choice because they pose a less strict limit on the obstacles, and also playing with the actuators, so you can choose how to pose the main body with respect to the terrain, so parallel, higher, or lower. And also wheels are more likely to damage terrain in some situation. So it has been chosen to implement a bio-inspired robot with 6 legs. Why 6 legs? Because to maintain the balance in a stable way, we need the 3 legs, and that the center of mass of all the robot is inside of the triangle designed on the ground. So to implement the movement, we need at least 4 legs. So 6 legs are more redundant, and they are good because they can permit to choose between various gate, considering velocity, instability, and also with respect to the steep of the terrain. So following the bioinspiration, each leg is composed of three elements with as many degree of freedom, coxa, tibia, and femur, where the joint with the case and the coxa is the vertical one, which is responsible for the advancement of the robot, and the other one are horizontal, and they are responsible of balancing the case, resulting in, as I said, a lot of actuator, 18 degree of freedom. So the ground segment was initially simulated, as we can see, and a setup of the same order of magnitude of dimension was acquired. Sorry for the black on black, but that's my desk. And after that, we had an estimation of the weight of the system, and we went to the aerial movement design. So having this commercial hexapod, it weight with all the electronics and cables, 2.4 kilograms, with 1 kilo payload capacity. So we considered a lava tube height of 50 meters and a descending velocity of 0.5 meters per second, resulting in a first thrust needed of around 6 Newton. After that, we choose 2 retro thrusters. Specifically, we did the calculus with the specific of this retro thruster here, B20 from down aerospace, which work with which are bipropellant thruster and work with nitrous oxide and propellant. After doing the dimension, the sizing of the tanks, we add the total weight of the system with like only, I would say, only 7 kilos, and a total thrust needed of 12 Newton. So here we can see some of the specific, also the thrust result really compact. And of the same order of magnitude of the dimension of the hexapod. So the mission design concept is explained by this really real draw picture. So the idea is to use a model rover who can bring the hexapod, the drone, near the surface, near the pit opening of the pit, and then after that, the drone drops the descend inside the pit opening and drops the base. So, like the vertical movement system is a one-shot system. It drops the aerial segment, and then it goes inside the lava tubes. And after a bit, it stops and starts to collect all the data he needs. After collecting the data, it could return to the pit opening to recharge using the sunlight, or to transmit the data to the base, which is envisioned as a router between the drone and the mother rover. Of course, this is a really preliminary design, and will be done more studies about also the communication techniques inside the basalt. And in the end, I conclude with the next step. Next step will be, of course, to lighten the setup, because now the commercial setup has a lot of component that we don't need, and also because it's in acrylic material. After that, the simulation will be updated with the new dimension, the new weight, and the real design of the ground movement, and there will be done a lot of simulation of various type of terrain. Based on that, will be finalized the aerial segment, as well as the power and telecommunication system. And in the end, we hope we will test that on relevant volcanic environment. Thank you for your attention.
Thank you. We actually finished in 10 minutes, so
yeah?
we have plenty of time to
okay.
ask some questions. Any questions from audience? They're quite interesting. Yes, over there.
I went too fast.
Yep. Oh, choose the podium. Paul Bremner, NASA Marshall Space Flight Center. So I'm just curious about the hexapod legs on the joints. Has there been any testing for dust that's affected by lunar dust?
We have at university we have a thermovacuum chamber with some kind of regolith simulator. So I think after the real construction of that, we will use that to simulate how the dust can interfere with all the lag, and also I like in the final design they will be all covered, of course, because they can't be open in an open environment.
Yep. Okay. Thank you.
Thank you. Any other questions? Yeah, over there.
Hello, Guillaume Ricard, Politique in Montreal, Canada. Have you identified any Earth-based outdoors occasions for tests? And when would you be planning to actually run field deployments? Thank you.
Okay, there's of course in Italy there's the Etna, where we could go to test. Also, there's the idea is to go to the Canary Island, to Lanzarote, where there's some test bed for this kind of experiment, I think. But it will be a thing like I am a first year student, so it will be like a thing of the third year me. So yeah, we will see.
So we have a comment from an online viewer. Let me just read it and maybe just comment it. So the problem with exploring underground cave on Mars is the issue of planetary protection. So I think non-contact exploration would be desirable first for the exploring underground caves on Mars. Drones with the legs are very interesting, but in this perspective, I think it would be a bit of a waste to give drones legs. I think we first need to further research the method for non-contact exploration of underground Martian caves using drones without legs. What do you think?
I don't understand if no contact it means that he has to fly, or no contact in general, because I think that no contact in general is a little bit risky for what I think, because if you don't know how much they can be high, you can go with a drone, for example, in Mars, because you don't know how much space you will have to fly.
Well, the comment looks like suggesting to go for the exploration without legs, so
with wheels. Yeah, I don't know. I think that yes, of course, but as I said, on some parts legs are better, because they are more versatile, and also if you want to do something compact like that with wheel, you have a really strict limit on dimension of obstacle, I think, because if the obstacle is bigger than the wheel, you can't surpass it.
Right.
But with leg you can.
Okay. So actually, I have a following questions. Have you ever considered other types of descending method rather than using thrusters?
Yeah, we were thinking about also using tether. So it would have been better regarding communication and also power management. But it has to be studied because it could add more weight because there will be all, of course, all the data of the data weight, and it could mean that we need the bigger models, and so all the design will be bigger, and it will be like a consecutive thing because then you will need more data, and then
Okay. Yeah, thank you.